Okay, let's look at our planar equations of equilibrium. Summations of forces in the x equals 0, summation of forces in the y equals 0, and summation of moments about some point equals 0. So all total, here in that situation, we're going to have three equations we can work with. So we can solve problems with up to three unknowns. But we can use other combinations. For example, we could sum forces in the x direction equals 0, and then we could sum moments about a point A in our body equals 0, or even outside our body, we can sum moments about another point equals 0. Or we could use just all moment equations. Some moment about A, some moment about B, some moment about C. Each of these individually would need to be equal to 0 for our body to be in equilibrium. Say we want to find the tension in our rope here and the reaction at A in this simple little problem. So first off, let's begin with a free body diagram. Now that was weird. That started off blue and then it switched over to white. So for our rope, we might have something that looks like this. As our rope, and we're looking at like tension T. With loading of 100 pounds. We would also have the effects of the pulley. So it would be a distributed type load here, where the pulley pushes up on our rope like this. Okay, so that's the free body diagram for our rope. And then we would have another free body diagram for a pulley. And our pulley would have a reaction at a y direction and a reaction at a in the x direction. And again, it would have this unusually shaped distributed load due to the rope on it. Well, that's too complicated to solve. Let's try combining those two into a bigger free body diagram. It would look something like this. So again, we're going to have AY and AX here. We have to represent now, we're going to combine these two together. Represent the load here of 100 pounds. And then we also have a load in this direction of T. We should have actually put up here 30 degrees. And we'll do that down here too. 30 degrees. So a couple things here. First off, I'm not going to model the weight of the pulley because the weight of the pulley is going to be canceled out by the support if this is not moving directly. So it's a redundant load that we don't need to really model. Another way to look at this is you could assume the pulley is weightless, or you could think that this is in, if this system is in maybe a y, and an x frame, and z comes out of the board, and z is the direction of gravity. So gravity doesn't have an effect on this system. So that's another way of potentially making assumptions here. The other assumption is that the rope, of course, is weightless. So these are the sorts of assumptions you'll need to make when you're solving problems. So let us now look at equations of equilibrium to solve what we're required to solve. Well, one of the things is to find the tension in the rope. That's tension T. Now, of course, our intuition might tell us that's got to be the same tension as is over here, so it has to be 100. But let's solve this and see what we get. So you want to judiciously choose your equations of equilibrium to use to do different things. And right now, since I'm solving for t, let's choose an equation that eliminates all the unknowns from the equation I'm going to use, where the unknowns don't exist, and that way I can easily solve for t. And an equation I can see right now that would do that is if I were to sum moments about the support A equals 0, because it's going to eliminate these two reactions. They won't be in the equation. So what's left is, and one thing I neglected to mention here is that the pulley has a diameter of well, let's just say it has a radius equal to 0.5 feet, half a foot radius. So now I can do my moment equation. So I've got 100 pounds times a moment arm. So if this is, each of these are 0.5. So this is 0.5 moment arm. And then I've got this, and I can have, even though this is at a different angle as this, so this was my moment arm, 0.5 here. This has a moment arm here, obviously, and it's the same distance, 0.5. So we have minus t times 0.5. So this just reduces to, with algebra, t equals 100 pounds, as we suspected. Okay, so we need to find AX and AY. So let's look for the AX first. So let's sum forces in the X direction equal to 0 equals minus AX. That just is straight up in the X direction. And then 100 pounds in the AY don't come into this equation, but a component of T does, and that component is plus T cosine of 30 degrees. Actually, now that I look at it, 30 degrees is here, and this is the opposite side, so this will be T sine of 30 degrees. T sine of 30 degrees. So I solve this equation, and I'll end up with AX equals 50 pounds. Okay. So there's 50 pounds of force on the pulley in the X direction. And it's in the direction that I have there, so it's actually still in that direction. Finally, let's sum forces along the Y axis. And what do we get? Well, we've got 100 pounds here, and it's in the negative direction. Although I drew the axis like that, I think I want to draw, let me flip it around. More natural to draw the positive y-axis in the up direction. So I'll end up with minus 100 then if I do that. But AY is positive. AY, and this component here will be negative, minus T, and this time it is T t cosine 30. So AY turns out to be 187 pounds. And that's our answers.